everyone. My name is Martí Caro. I'm a third-year PhD student at the Computer Architecture and Operative Systems group. And well, today we'll present this paper that was published recently at the Embedded Real-Time Systems Conference. And well, the title of the paper is Software-Only Semantic Diverse Redundancy for High-Integrity AI-Based Functionalities. And well, I've made this work with the help of my PhD advisor, Jaume Abella, and also Axel Brando. So, well, let's start with a bit of background on the main topics of this work. So basically, artificial intelligence is increasingly used in safety-critical systems to enable autonomous operation. So, for example, in autonomous driving cars, in rendezvous and docking operation in space, or in pilot monitoring in avionics. However, the AI has been used so far mostly in fail-safe systems where the AI software did not inherit the safety requirements. But the AI in these systems, in autonomous systems, can be in charge of very high integrity operations like braking, steering, and docking. So for this reason, in this kind of systems, it often requires the highest safety requirements, which are, for example, delay in avionics or ASIL-D in automotive. So in this work, we are focusing on camera-based object detectors that are basically based on deep learning algorithms. We were focusing on the perception module, which is in charge of detecting the objects that are surrounding the vehicle. And in particular, we use the you only look once, or YOLO for short, which is an efficient real-time camera-based object detector. In this case, we're using the YOLO version 4, which is a CNN that is made of 161 layers. And it can detect 80 classes of objects, although we will only focus on those that are relevant to our case study, that is autonomous driving. So the task at hand, in this case, is object detection, which basically the model has to give a bounding box for each object in the image, which is basically a rectangle that is surrounding the area of the object, as we can see in this image. It also has to classify all the objects. So for example, here it's detecting some cars, and it has to give a confidence value for each detection, which is basically a value between 0 and 1, saying how sure the model is that this is an object. Then, well, as I said, this kind of systems require very high safety requirements, which basically impose redundant execution as a mandatory safety measure. But we have to be careful about how we implement this redundancy, because there are the so-called common cause failures, which are basically faults that can affect redundant copies analogously. So we need some kind of mechanism to avoid these kind of errors. So for this reason, we need diverse redundancy, where we add some kind of diversity to our system, so that now we have different outcomes. Both can be potentially erroneous under the same fault, but since they are different, we can detect that there has been a fault. Then we need to take into account that camera-based object detectors need to generate a new object list around 40 milliseconds, which is a rate of 25 frames per second, which is more or less what we need for real-time operation. And while this entails very large energy and bandwidth costs, which are a key factor in this kind of systems. So for example, in this case, with YOLO, we have that the DRAM read bandwidth and the energy is huge, which is around 80% of the total. So an efficient diverse redundancy mechanism must not increase this DRAM read energy. This means basically that the input data should be shared across the redundant components. And to protect this data, we can use error correction codes. So now I will explain the typical implementation to obtain diversity, which is the Triple Modular Redundancy, or TMR for short, which basically consists in executing identical operations in 3 compute units. As we see here, for example, we have compute unit 1, 2, and 3. And then the input data, which are the image and the weights, are basically shared across the redundant components, because if we had to refetch all this data, it would significantly increase the energy consumption, as I previously mentioned. So then to obtain this diversity, what we do is add a short delay, which is here specified with this delta and 2 delta to each of these computing units, so that we can avoid having identical states at any point in time. So we can avoid these common cause failures. And then basically what this will do is it does a majority voting for every operation, right? Comparing the outputs at bit level. And then the output data is sent to memory just once. So basically the final detection. And well, in this work, we're proposing an enhanced TMR mechanism that provides fault tolerance against random hardware faults, for example, due to radiation, but also it provides tolerance against the model inaccuracies, since these models are not perfect, as we will see in the evaluation. So then we ask ourselves this question, if bit-level redundancy is really necessary, because in fact, the algorithms that are using these detections don't really need perfect bounding boxes and 100% confidence scores. So as long as the estimated bounding boxes are more or less, or approximate the location of the object, and the confidence is above a certain threshold, which is usually set to 50%, then the detections can be regarded as semantically the same, let's say. So they are in fact, in reality, the same. So for example, if we take a look at this image, we see that there are 3 bounding boxes for the same car, but we see that any of these would confidently avoid a collision against the car, even if they are not the same bounding boxes, and the confidences, as we see here on the right side, are different. So in fact, we see that any of these 3 detections are semantically the same. So then now we will explain our enhanced TMR mechanism. Basically, YOLO version 4 may require fetching several gigabytes of weights to process each image, whereas the image occupies just a few megabytes. So basically, our redundancy scheme wants to preserve the same DNM model to avoid having to duplicate or triplicate the number of weight fetches. And basically, we build our redundancy scheme by altering the input image data, which basically would map to this f of x, g of x, and h of x that we see in the image on the bottom. And then the outputs are expected to remain identical, semantically speaking, but not identical at bit level. So basically, what we will do is merge these outputs using different algorithms that provide different trade-offs, as we will see later in the evaluation. And well, note that we need 3 parallel physical compute units if we want to achieve the maximum performance. But if that's not an option, we can implement this purely in software means by simply executing the 3 inputs in parallel in a single GPU. Then, well, we have considered different image transformations that are provided by the Clotza Open Library, which would map to this f of x, g of x, and h of x that I mentioned. I will not go into detail about all these transformations, but basically, so you can see visually the impact of this. We have some photos here on the right side. So we have the original image, the horizontal flip, the medium blur, which basically adds a bit of blur to the image, and the equalization. Then we combine those predictions that basically have the same class. So we're combining cars with cars, not cars with person. And also whose bounding box is more or less similar so that it can be regarded the same. Then we have evaluated 3 algorithms to merge these predictions, which we have named with voting, averaging, and maximum. And now I will briefly define a bit what we do with each of these algorithms. Basically, to set the confidence with voting, we take the maximum confidence amongst the detections that are being voted. With averaging, well, as the name suggests, we simply do the average. And with maximum, we take the maximum. And then with the bounding boxes, with voting, we basically retain the bounding box of that detection that had the highest confidence. With averaging, again, we simply do the average. And with maximum, this case is a bit more special because we can have, let's say, redundant bounding boxes, since we're taking the maximum across all the redundant components. So for example, we can have that each redundant component detected the same car, but as we see, the bounding boxes are not the same, right? As I said before. So basically, in this case, what we do is we apply a non-maximum suppression to filter out these repeated detections that basically compares the bounding boxes that have the same class. And then if the intersection over union is greater than 0.5, it will just take the one that has the highest confidence. So for example, in this car, we see that before the NMS, we had 3 cars with 90, 87, and 95. And then we will just take the one with the highest confidence, that is this 95. Then regarding the evaluation setup, we used a 32-bit floating point TensorFlow Keras implementation of YOLO version 4. We use the publicly available pretrained YOLO version 4 parameters. That basically this was trained with the COCO dataset. And then we have evaluated our proposal with two network sizes, with the default that is 608 times 608, and then also a reduced version that is 320 x 320, that basically gives 2x inference speed at the cost of a bit of accuracy loss. Although on that evaluation part, I will not go into details about the 320 by 320, because basically the conclusions are the same, so we'll just focus on the main one. Then we evaluate our proposal with the COCO dataset using the validation subset, not the training, because that was the one used to train the model. And we only keep those images that are relevant to our case study, which is basically vehicles and pedestrians, which gives us 870 images. Now, the issue, let's say, with the COCO dataset is that it's not very specific to autonomous driving, which may limit a bit the conclusions of this evaluation. So as we see in the image, we see that, yes, there are cars, there are pedestrians or people, but this image is not the same as a car driving on the road, right? So for this reason, we have also evaluated the Kitty dataset, which is designed specifically for this kind of applications. But again, I will not go into details about this evaluation, just to keep it short for this talk. But the conclusions are basically the same with one dataset and the other one. So then let's talk a bit about the evaluation metrics. In this case, we're using the accuracy, or ACC for short, and the mean average precision, or MIP. Basically, these metrics are built on the intersection over union, which basically is the intersection of the area between the ground truth and the predicted one by the YOLO, divided by the union between these areas, basically. And then this will give us a value between 0 or 1, 0 if they don't even intersect, and 1 if they're exactly the same. And we can set a threshold, for example, 0.5, and based on this, we regard them as the same, right? So if they have this IOU greater or equal than 0.5, we say that they can be considered the same bounding box, which is basically one of the standard metrics to use. Then using these metrics, we can classify the predictions as true positives, which is basically a correct detection, right? That YOLO detected an object. A false negatives is a detection that YOLO did not detect. And a false positives is something that YOLO detected that doesn't make sense, that doesn't exist in reality. Then the ACC is calculated as the number of true positives over the sum of true positives, false positives, and false negatives. And the MIP is quite more complex metric that I will not go into detail, but basically leverages discounts to obtain a single metric for each class. And then it does an average of these individual classes, individual scores, to do, to obtain a final accuracy metric. So then let's start with the evaluation. And here, first of all, we see the results of the independent configurations. So basically, we only have one component, and we're applying the image transformation, right? So we have here in gray, we see the baseline, this BL, which has an MIP of 60.87. And then we see some transformations that are interesting. For example, vertical flip doesn't work well at all. We see that it only has 5% MIP. Basically, this is because the pre-trained model is not trained to detect vertically flipped objects, so it's not able to detect this. And then we also see that there are some transformations, such as top shift, raise value, horizontal flip, and left shift, that gives us a bit of MIP increase with respect to the baseline. And then here I'm showing the results of the merging algorithms. Basically, this figure is showing the sorted it's sorted independently for each merging algorithm, which basically means that the FBS configuration for one algorithm may differ for the other ones, but having the data in this format allows us to obtain some conclusions. So basically, we see that maximum, which is this blue dotted line. This provides consistently the best results in terms of MIP. Across all configurations, we see that all of them are greater than the baseline, that is this red straight line. Then we see that the averaging is consistently worse, as we see is this gray line. All of these configurations, these combinations of transformations are worse than the baseline. And then we have voting, that is this orange line, and we said there are a few that are better than the baseline. So then in this table, I'm showing the top 5 MIP configurations for each algorithm. So we can see some of these combinations that are interesting. So first of all, we see that these shifting transformations, which are basically the left shift, top shift, right shift, and bottom shift, we see that these work particularly well with voting and also with the maximum merging algorithm. For example, if we look at the maximum, the first one that is HF, RS, and BS, we said it obtains an MIP of 66% compared to the baseline that is 60%. So we have more or less a 6% increase. And in the voting, we have more or less a 1% increase. And then with the averaging, we see that the baseline, having 3 baseline works particularly well, but we are not adding any kind of input data diversity in this case, since we basically have 3 baselines, so no image transformation. So basically what we see here is that in this case, with averaging, doing the image transformations doesn't give relevant results. And then if we look a bit more into the results, we see that voting may increase a bit the true positives, right? As we see the baseline had 3,800 something, and now we have like 40 more true positives with the first configuration. And it also decreases the false positives. So basically it's outperforming the baseline in all fronts. So we have more true positives, less false positives, and we have more ACC and more MIP. And on the other hand, we see that the averaging basically tends to decrease the true positives, but it fails to decrease false positives significantly. So basically you obtain worse results with all the metrics. And then with the maximum, this one tends to increase true positives, which is good, but it increases also the false positives, which is bad. But still we see that this combined effect clearly increases both ACC and MIP. So we're getting more true positives than false positives. So then regarding the fault injection framework, we are focusing on random hardware faults that impact the computation, which are called transient faults. And we have injected these faults in the result generated by multiplications and additions of convolutional layers, which are basically 99% of the operations. And then we have only considered to inject these faults in the sign or the exponent of the floating point, which is basically the 9 highest order bits, since random bit fields in the mantissa are mostly masked and don't lead to any changes in the output of the model. So then if we look at these tables, we'll discuss the results of the fault injection. In this table, we show the results of our proposal in non-faulty TMR cases, as well as in 2 faulty cases. So we have the first case, which is with independent faults, where this means that for a given image, only one of the 3 components is affected by a fault, right? So only one per image. And then we have the second one, which is false in the same image for all 3 components, which is a more extreme case. Then in this table, we are only showing 2 configurations for each merging algorithm, which basically corresponds to the maximum, well, the configuration that has the best ACC and the best MIP. And if there's a case where one configuration had both the best MIP and best ACC, we are showing here the second one that has the highest MIP. Then if we take a look at this table in the fault-free scenarios, which would basically correspond to almost 100% of the time, since the random hardware faults are very, very rare, we obtain the following conclusions. We see that voting and maximum merging algorithms provide higher MIP and ACC than the baseline. And then again, we see that the averaging basically is producing consistently worse results than the baseline. Then if we take a look when the faults occur independently, so only one of the 3 components has the fault, then we see that with voting, it's still providing higher MIP and ACC than the baseline. It has reduced basically just 0.10% more or less, or 0.4%. So it's a very small MIP decrease. And then with maximum, we have similar conclusions. It's basically still higher MIP and higher ACC than the baseline. And then finally, with averaging, it wasn't working well in the fault-free case, so it's expected that when we inject faults, it's also producing more results than the baseline. And then finally, for the second case, if we look at when the faults are occurring in the same image for all the three components, which is the most extreme case, we see that maximum has at least one configuration that has a higher ACC. And well, in the case of bolting, all of them have lower MIP and ACC, but we said still the accuracy is quite close to the baseline. And with averaging again, it simply produces worse results than the baseline. So basically, to conclude this evaluation, we can say that averaging is consistently worse than bolting and maximum in all cases, and it's worse than the baseline. Then we see that maximum produces the best MIP results by far, but it also has this downside that it's providing significantly higher false positives, which may not be that good for certain applications. So then if these false positives are a major concern, then bolting would be the best solution overall at the cost of less true positives, but we also have less false positives. So then we have also implemented an open source diverse redundancy tool that basically allows users to replicate all of our experiments. And well, the users can easily experiment with other image transformations. They can modify it however they want. It's available on the GitLab, on the BSC. And basically, we're implementing DMR and TMR redundancy in GPU. To test this, we use the NVIDIA Orin that is available to our group. And basically, it has the option to execute 2 or 3 components simultaneously. And you can specify the image transformations to use, the output merging algorithm. So if you want to use the average, the maximum, the bolting, you can also specify if you want to do fault-free or fault injection experiments. And well, as I said, adding new image transformations is quite simple and is explained in the documentation. So then to conclude, AI software is increasingly used in safety critical systems for these functionalities where the AI software inherits safety requirements. So whenever these requirements relate to the highest integrity levels, we must implement diverse redundancy mechanisms, for example, the TMR that I explained. However, these existing solutions that are based on lockstep processors provide diverse redundancy with bit level error detection and correction. But as we note, there are abundant functionalities that actually don't really need bit level correctness. In fact, semantic correctness suffices. And basically, we're leveraging this observation to present a diverse redundancy scheme based on applying binary transformations to the input data, such as we saw, like horizontally flipping, adding some blurring, or things like this. And this allows us to mitigate random hardware errors and also some AI model inaccuracies. And while we are currently exploring the effectiveness of this solution to mitigate the impact of adversarial attacks, and we plan to get a paper on this as well. So basically, we'll use the same idea applied to a different concept. And that's it. Thank you for your attention. Yeah. If there are any questions?